Okay, so let's just read this problem. So an object is moving on a horizontal line and it has the position, right? So we're told that this is a position function of x of t equals 5 cosine of t miles per hour in this time interval from 0 to 2 pi. Okay, cool. So we know this is position. X of t is equal to 5 cosine of t. Now, the first question is asking us, at what values of t does the particle change direction? So question for everyone, if we're looking at when the particle changes direction, are we going to be looking at position? Are we going to be looking at velocity or acceleration? Which one are we looking at? Okay, Aaron, you want to come off mute?
I think we look at the velocity because the velocity is a change in position.
Yeah, that's a really good way to put it. So yeah, again, velocity is a change in position. So if we're changing direction, right, if we're suddenly going from right to left or left to right, we're going to be changing position, right? So looking at velocity is the best way for us to tell that. So we're going to be looking at velocity. And can someone come off and tell us what x prime of t, because that's what velocity would be equal to, what x prime of t is equal to? So taking the derivative of 5 cosine of t. Daniel?
Gonna be -5 sine t.
Yep, that's exactly right. So -5 sine of t. Now we want to find where velocity essentially, right? So we're looking at where this particle changes direction. So where the velocity is like where the particle is going from one direction, right? So let's say it's going to the right, right? So the velocity would be positive, right? And then it's going to change going to the left. So the velocity would turn negative. So we're looking for where the velocity goes from positive to negative or negative to positive. Now, what does that mean? It means that at some point, the velocity is going to have to be 0. So we're really interested in where the velocity is 0, and then we can kind of fill in like how we do with like maximums and minimums to see where the velocity actually changes. So we're going to look for zeros. So -5 sine of t, and then we're looking at this specific interval from 0 to 2 pi. Now, if we simplify this, it's basically the sine of t is equal to 0, right? Because we're dividing both sides by -5. But can someone tell me on the interval from 0 to 2 pi, some trig refresher, where is sine of t equal to 0? And you can just type this in chat if you want, or raise your hand. Awesome. So, okay. Thanks, Kayla. Thanks, Mercy. Thanks, Aram. Yeah, so there's actually 3 answers. So thanks for everyone who shared. There's actually 3 answers. So at 0, pi, and 2 pi. So if you think about the unit circle, right, sine of whatever is y over r. So we're drawing this line, y is equal to 0 at 0, right? At pi, right? If I draw in a line, y is also equal to 0. So 0 over r is 0. And then at 2 pi, so I'm back here, right? Y is equal to 0. That's probably not the best sketch, but hopefully you remember like sine of whatever is like y over r, right? Okay, so at 0, pi, and 2 pi. Well, if we're drawing this interval, right, let's draw a number line now. Right, pi is in the middle, 0, 2 pi. Well, there's only really one place where it can possibly change direction because 0 and 2 pi are they're at the ends, at the limits, right? So if I plug in anything between 0 and pi, I'm just gonna into our velocity function. I'm just gonna write this down. We get a positive number, and then between pi and 2 pi, we get a negative number. So this tells us that at the point pi, the velocity changes from positive to negative. So the particle direction changes from, let's say, going to the right, and then at pi, it starts turning around, it goes to the left. So at t equals pi is our answer. There is a change in direction. Now, using this, we can pretty easily tell. Can someone answer what part B is? You can just answer this in the chat, or raise your hand. Ansel, you want to answer this question?
No, I had a question.
Okay, go for it.
When you change when you change from the positive to the negative, right? Was that because when you're from 0 to pi, the y is positive, and from pi to 2 pi, like the y value on the coordinate is negative?
Are you really talking about the unit circle?
Yeah. So is that how you got like a positive on this side and a negative on that side?
Yeah. So you could always just plug in a number if you have a calculator, because I'm pretty sure like on the test, actually there's only a calculator portion. So I don't know. I just thought about plugging it in, but yes, you could look at the unit circle, right? And then from 0 to pi, which is this area, right?
Mm-hmm.
If I draw any value, right? Let's say this line or this line, you're right. So the y is always going to be positive, right?
Mm-hmm.
So y here is going to be positive. So if I'm going to have a positive number, right? So y over r is going to be positive, right? Because y is positive, and r is always positive. R is always just 1. So it's going to be a positive or a positive. So we're going to have a positive number. Then if we look down here from pi to 2 pi, right, this area from pi to 2 pi, right, let's say I draw some random value, y is always negative, right? So y here, y is always negative, you see, because it's going down. So y over r is always going to be a negative number, over r is always this positive 1, so it's always going to be negative. So yeah. Yeah, so your way of thinking is correct. So can I get an answer for part B? On what intervals is the velocity of the particle positive? And you can tell this just directly by looking at our work for part A. Thanks, Damani. Would you be able to come off mute and just really quickly share how you know this answer, how you got this?
I got this answer because I looked at part A, and from 0 to pi, it's positive.
Yep, exactly right. So that's all you have to do. We did this. We did all the work we needed to do in the first part. So from 0 to pi, we see that the velocity. Remember, this is a chart of velocity, right? And this is v of t or x prime of t, however you want to express it. So from 0 to pi, we have a positive velocity. Okay, cool. So now I'm actually going to have people attempt part A of this problem. And once you get an answer, please just chat your answer into the chat. It should just be like a number. And I'm going to give everyone maybe 2 to 3 minutes to do this. So please begin. Part A of this problem. Actually, this probably takes less than 2 minutes, but yeah. make sure to read the question very carefully. Samantha, I did see you get your answer, but actually just try to reread the first part because it is like they do kind of try to trick you. Awesome, thanks, Kayla. Okay. Yeah, I'm seeing. Yep, Samantha, that's right, exactly. Cool, yeah, I'm seeing a lot of people like, you guys are definitely doing the calculus correct. This is just a problem where they kind of try to trick you with the wording. So I'm seeing a few people fall victim to that. Okay, it seems like most people have finished the problem. So when looking at this problem, when I first read this, I see that the velocity of an object in motion is given by the function blah, blah, blah. The units of velocity are miles per minute. Well, the first thing I notice is that this says velocity. It does not say position, right? We talked about how the relationship between position, velocity, and acceleration works. They seem like they already skipped a step. They don't even tell us what the position is. They straight up tell us this is velocity. So this is already basically, if we want to think about it, this is like the x prime of t question. So give me 1 second. Okay, so the function that they gave here, v of t, is already the x prime of t. So x prime of t equals v of t. It's already the velocity. So 3t squared minus 36t plus 9. Sorry, give me 1 second. Sorry about that. Again, so we're looking at this. This is already giving us a velocity function. So literally all we have to do is plug in 0. So we're just finding v of 0 is equal to 3 times 0 squared minus 36 of 0, etc. These all cancel out. So it's just 9 equals 9. So, and then we're told that the units for velocity are miles per minute. Remember, the units for velocity is always going to be a change in position, which is miles, over a change in time. So it's miles per minute. Cool. So I would like everyone to take now 1 to 2 minutes to figure out part B. And some of you guys kind of already solved for part B in part A. But please take the time to now solve for part B. And once you get the answer for that, please send it to me in chat. Cool, thanks, Kiana. Thanks, Mercy. Yep, seems like you guys are on the right track. Thanks, Christian. Awesome, thank you, Aaron. Renique, good job. Give everyone maybe 30 more seconds, maybe a minute. Awesome, Aaliyah, good job. That's right. Okay, cool. Kiana, could you come off mute and tell us how you solved the problem? Are you able to come off mute, Kiana?
Hello?
Hello? Hi.
Okay, so I found the derivative of the first function they gave us, and I got 6t minus 36.
Gotcha. And why did you find the derivative of the first function?
Because we know that velocity is supposed to be like the derivative of the position function, and they already gave us that. And then acceleration is the derivative of like the velocity or whatever. So
Yep, exactly right. So remember, we're not trying to find like the double derivative of this anymore, right? Because they already gave us velocity. So we just have to move up one step basically. So find one more derivative. So we can say the acceleration function is equal to the derivative of the velocity function. And then you told us that was 6t minus 36, right? Cool. So now we're just going to plug in 0. So v prime of 0 is equal to 6 times 0 minus 36. So it's equal to negative 36. And Renique, would you be able to come off mute and tell us what do you think the units would be for this problem, for our answer? So we know for the first one it's miles per minute.
Is it is its velocity over time? I don't know.
That's actually a really interesting way to think about it. So so I'll just give the answer. So it's, remember, it's actually, so you just take the velocity unit and then you take the denominator and square it. So it's miles per minute squared. You're just going up another level basically. But in a way it is taking velocity over time again, because you're again, acceleration is basically this change in velocity. So change in v over change in time, right? That's what we looked at before. So it is, in a way, it is velocity over time. So if you think about it, it is miles, like this is velocity is miles per minute, right? And then if we want to do acceleration, we're going to do it all over a minute again. So that's actually kind of why we get miles per minute squared. Right? So if you do miles per minute, that's velocity. And then we're finding that over the change in time again. So we need to divide it by a minute again. We're getting miles per minute squared. So that's like an explanation of how we get the units for acceleration. But I think it is a bit confusing just when you look at it. You're like, miles per minute squared, what does that even mean? It's probably more helpful just to memorize it. So the units for acceleration is going to be like a certain distance over a time unit, square it, and then you square the denominator. So yeah, I think I'm going to do part C really quick because I think everyone should get this. So we take the acceleration equation we just did, right? So 6t minus 36, and then we're going to set that equal to 0, right? So it's going to be 6t is equal to 36, t is equal to 6. So at t is equal to 6 minutes, acceleration is 0. And what that means is that the change in velocity at this moment is 0. If I just want to make that more clear. So the change in velocity at this moment is 0 when the acceleration is 0. Okay. So yeah, I'm going to give everyone like 15 seconds or so. I'll give everyone like 25 seconds to copy anything that they might not have written down. Okay, so now I'm gonna look at this second problem, and I'm not gonna ask you guys to write it down actually, because I think it's a bit too much. I just want people to read the problem and to try to answer it. It doesn't require any math. And once you think you have an answer, please chat your name. So again, this is the real question. Interpret the equation. We don't have to do any math. They're just asking us to interpret if we got this answer. Like, what does that really mean? Thanks, Aaliyah. I'm gonna give everyone like 30 more seconds. So. Okay, Aaliyah, would you be able to come off of mute and answer this question?
Yeah, I think that the c prime of 5 equals 4. I mean, I know when you take the first derivative, it's the velocity. And so maybe like when you just take the first derivative and then you plug in 5 so that it will equal 4. So I guess that means that at, like, I don't know how to put that in context of velocity. Like at that certain point in the velocity at 5, what is it? What's the time? 5 hours. It will be charging at a rate of 4 or something like that, or like I don't know.
Yeah,
like that.
that's perfect. That's perfect. So this problem, obviously, we're not looking at position, velocity, acceleration, right? But we can kind of think of it in the same way. So we're told that essentially our position equation, which I'm going to call it position/charge equation, is C over T is equal to this whole thing, right? We don't really care what it is, C over T, right? So that's our position/charge. So basically I can plug in T equals 5, let's say, right? This is just C, this doesn't have a prime yet. There's no prime. So it's just C over T. I can plug in a 5 and it will tell me what position or what charge we're at. So I can plug in 5. In this case, it'd be like, okay, 5 doesn't even make sense because it would have a -5 charge, but that's besides the point. Basically, I plug in a certain time, and then it will tell me what the charge is. Now, if I take the derivative of this, so it's going to be velocity slash, I don't really know how to express this, charge over time, right? Because it's now we're looking at a rate. Now we're looking at like not just what the charge is, but like the rate of the charge. So how fast it's charging. So in this case, 4 could be modeled by 4. We're told that charge is in joules and T is in hours, so it'd be 4 joules per hour. So if I'm gonna, so the actual answer for me to write out in like a clear sentence is at T equals 5 hours, the Tesla is charging at a rate of 4 joules per hour. So by finding the derivative of the position/charge function, we're essentially finding a velocity function, which is 4 joules per hour. So hopefully that makes sense to everyone. I'm going to give 30 more seconds for everyone to copy this down if that helps. Although you guys didn't really copy down the problem, so shouldn't be like, just try to understand this. Okay, I'm going to move on now to, this is the first part of an FRQ. We only have 7 minutes left, but I'm going to give everyone 3 minutes now to try to solve part A. So again, make sure to carefully read the problem and then try to solve part A. Once you think you have an answer, you can either message/chat your answer to me or just chat your name. I think for this problem, it's going to be finding the actual derivative that might be the most challenging part. But if you're able to do it, it's great. Two more minutes. Maybe a bit less, actually. I'm going to give maybe 20 more seconds. I only have an answer from Reese so far, so thank you, Reese. Yeah, this problem might be kind of challenging. Okay, so there's only 4 minutes left, so Zakaya, if you still need the notes from me scrolling up, I can do that after class, but I'm going to try to finish this problem really quick. Okay, so Reese, could you come off mute and tell us like what your first few steps were?
So basically I wrote down, at first I wrote the velocity, which is, I forgot what it's called, but what's that sign called again? I think that's inverse log, right?
That's natural log.
Natural log.
Natural log. Yeah, so yeah.
I found the derivative of what's in the parentheses, so I did natural log of 2t minus b.
Okay, so to be clear, to find acceleration, how many derivatives did you do?
Oh, I did it
Like
once because that's like the first derivative already.
Yep, exactly. So velocity is already the first derivative. So it's the same as the previous problem. We're already given velocity. So acceleration is going to be equal to just the first derivative of velocity. And then, okay, thanks Reese for sharing. Yeah, Kiana, would you want to come off mute and then like discuss how you actually got the derivative for this one?
Okay, so I used chain rule. So
Mm-hmm.
I did natural log times 2t minus 3 plus 1 over x t squared minus 3t plus 3.
Gotcha. Wait, so how could you kind of clarify 1 over x? How did you do that?
It was in our notes from earlier. I just remembered that we wrote it down, that the
Okay.
derivative of, yeah.
Okay, so there's only 2 minutes left, so I'm going to run through this really quick. So hopefully you guys remember that the derivative d over dx of natural log of x is equal to 1 over x. That is an identity that hopefully you guys will remember. So when we take the natural log of t squared minus 3t plus 3, our first step can just be to use this identity. So we're going to do 1 over and then just put everything in the parentheses, right? Because that's what they did here. They just took everything like the x and just put it like as an inverse function. So 1 over t squared minus 3t plus 3. But then Kiana brought up a great point that we're not done, right? So although we did this identity, there's still a chain rule because we have this function that's within a function. So the t squared minus 3t plus 3 is within the natural log. So we need to derive the t squared minus 3t plus 3. So I'm going to multiply this by 2t minus 3. So that is essentially equal to 2t minus 3 over t squared minus 3t plus 3, right? Just put this in the top. So after this, I can just kind of plug in 4, right? Particle at time t equals 4. And then 2 times 4 minus 3. Sorry for keeping everyone late. But 4t squared minus 3 times 4 plus 3. End of the story, we get 5 over 7. And then the units is in meters per second squared, like we discussed with the squared. So yeah, you guys can copy this down. Hopefully that makes sense. After you guys copy down this problem, there's the exit ticket. Please turn in your class notes. If you guys weren't able to like copy down word for word an entire problem, don't worry about that at all. I understand these word problems are like probably really tedious to copy down. So yeah, don't worry about that. And yeah, if you have any questions, I'm going to be staying after class. All right. Hi, Renique, do you have a question or?
I was just wondering, like,
Mhm.
do we have like, do you have like a study sheet or like a cheat sheet, like all of this terms and stuff on it?
Actually, I think I might, but it's kind of like, what do you want a study sheet on? Like just derivatives or?
Like derivatives, because derivatives is the problem for me. I can understand all of this extra stuff. I just can't did with the derivatives.
Like remembering like natural log of x and all this stuff?
Yes. No, it's
Okay.
not. It's not like the derivatives of a specific term. It's more like how to use the derivatives in like different situations and like El Hospital's rules, stuff like that. So like all of the rules.
Okay.
Yeah.
Gotcha. Okay. I'll say, Okay, is there anything you're like really confused on in terms of like when to use? Because I feel like I agree with you, like memorizing when derivatives, like memorizing L'Hopital's and all these different rules could be really annoying. But like being able to understand when to use it is like, I think that's probably more important.
Yeah.
So is there anything
It's
specific you like
like
struggle with that?
hold on.
Yeah, go for it.
Yeah, so yeah, I feel like it's just some questions like this question. When I was doing the extra ticket yesterday, I didn't think we needed to use a derivative. Don't mind my guinea pig in the back, but I didn't know that we needed to use a derivative. But
yeah,
it's like
I actually, no, I think the exit ticket, it's kind of deceiving. The exit ticket, because it's like just change in direction, I think. And it's like,
yes.
yeah. So I feel like even I could be confused by the exit ticket.
Because I was looking through my notes from last year, and it didn't like when the changing like direction stuff. It
Mhm.
was telling me that it changes direction when it hits the x-axis. So I just put like which points it was at when it reaches the x-axis, and I didn't know I had to like take a derivative
Yeah.
and then have to find yeah.
I will say, I think it will only change in direction once it hits the x-axis if you're looking at the derivative graph, though, right? Because that means like, if you're looking at the derivative graph, that means once it hits the x-axis, it's going from like a positive velocity to a negative velocity, or a negative to a positive, right? When it crosses that x-axis. So you are looking at the derivative graph at that point.
Okay.
So yeah, I mean, that's just to try to kind of clarify things, but yeah, I feel like, so at its core, I don't know if this is going to help in like 2 seconds, but a derivative is like an instantaneous rate of change. So I think like really just thinking about that, it's really just the slope at the end of the day, right? That's all a derivative really is. So like yeah. Yeah. So I don't know if that kind of
I'll
helps
just
at
try
all.
to
But
review and look over all of the terms and stuff in my notebook.
okay, thanks. And I'll try to get a cheat sheet out as soon as possible for derivatives, because you're right, that could be very helpful. Okay.
Yeah.
Thanks,
Okay.
Nick. Bye.
Have a nice day.
Yep, you too.